Hello, everybody, and welcome to the big one, the proofs practice page. So this lesson right here is going to be something that we use in every single lesson from here on forward, or almost every lesson. This is really what underlies all of geometry, is that we're not just working with shapes and finding area and stuff like that, but we're trying to prove how we know that things are true and false. So getting right into it, the idea of a justification is something we're going to be using in like all of these proofs. So I wanted just to make sure that everybody knows that justification simply just means the reasoning used to draw a conclusion. So like, how do you know that you're able to do a thing, right? These other two words right here, postulate and theorem, are specific to math or even specific to geometry, really, that we use a lot. Another word for postulate is axiom, and it's just information that we know to be true without needing a formal proof. Whereas a theorem is a statement that has already been proven to be true. So my favorite example when it comes to this is the idea of a triangle. So with any triangle, two pieces of information that we know, or at least I know, is that it's going to have three sides, and that the sum of the interior angles, so the interior angles sum to 180. Which that second part might not be obvious. The first one I bet everybody knows, right? The first person who ever decided what a triangle was knew that it had three sides. But moving forward from there, the idea that the inside angles, this angle plus this angle plus this angle on any triangle, even if I drew something, a completely different triangle, the interior angles would add up to 180. That's not something that's quite as obvious as saying that it has three sides. So this first one would be an example of a postulate, information that's just known to be true without needing a formal proof, whereas a theorem would be something that had been proven, such as that all the interior angles of a triangle add to 180. All right, so those are two words just to know as we move through. You're going to hear them a lot. And to start out thinking about proofs, I want to make sure that everybody is solid on the properties that Mr. Sheridan went over. So you looked at this in your last video, but again, just to make sure you're good with it, what I want you to do is go through and try to match each property with the example that's been provided here. So like, for example, saying that x is 3 is the same as 3 equals x is an example of the symmetric property. So each of these properties will be used once as you go through. I want you to go ahead and pause now and see if you can go through and fill in the rest on your own, and then we can go over them together afterwards. All right, so hopefully you took some time to fill those in. The next one below symmetric property would be the distributive, which hopefully didn't blow your mind too much. When you see a number outside of parentheses, you can distribute it into the parentheses. So that's the distributive property. Additive is where you take a statement like x equals 9 and you add something onto both sides. So if x equals 9, then you can say x plus 3 is the same as 9 plus 3. Reflexive is like the most useless one. It's used some in like really super formal proofs, but you don't need to use it very often. It just states that something is equal to itself. The division property is like the additive, but with division, right? You have x equals 4, and then you divide both sides by some number, in this case 2. Same thing with subtractive. You start with some equation, and you can subtract on both sides and maintain equality. If m is 12, then m minus 4 is equal to 12 minus 4. The multiplication, still building off that, if something is equal, you can multiply both sides by the same number and maintain equality. The transitive property is really useful to say that if one thing equals something and that something equals something else, then the first thing equals the last thing, a equals 4. We can kind of skip over that middle part and just jump from beginning to end. And substitution is really similar, that when you have a statement and you know part of that statement equals a thing, you can take that thing and plug it in to that first equation. So if x equaled y plus 3 and y is 2, I can plug that 2 in for the y and do 2 plus 3 to say x is 5. So that's the idea of the substitution property. Now, using these, make sure that you don't just look at it and say, oh, that's multiplication. It's the multiplication property. No, it's not what's going on in the problem. It's what you would use to solve. Like if I was going to solve this problem, what I would have to do is get x by itself. So I get rid of the multiplication by dividing. Right, x equals 9. So I'm using the division property so that I maintain equality. If 2 times some number is 18, then we know that that number is 9, right? That these are equivalent statements is the idea. I didn't just make up some new problem down here. I maintained equality by using the division property. So as we go through this problem, see if you can go through and use which of the properties, or determine which of the properties is being used to move from one step to the next to the next. The problem's already been solved. All I want you to do is fill in the justification for what was done on each step. So go ahead and pause and try that now. All right, let's check it out. So as they went through and solved, the first thing is you'll see most proofs, almost everyone you come across starts with a given, right? You take what information was given to you and you start by writing that in what's called a 2-column proof. And you just say that I know this is the problem we're working with because it was given to me. Seems a little silly, but we have to start somewhere, right? That's how we're going to start out. Now, how do I know that this equation is the same as the one that was given to me? Well, I know that they're the same because all that was done was the application of the division or the distributive property. Sorry, we distributed 2 times 1 and 2 times 3x. When you distribute, this distributive property of equality tells us that we're maintaining the same problem. I'm not just creating some new problem here. This is the same as that. It just looks a little different because I did distribution, but it's still the same equation. And the same thing's going to be true all the way through. When you look at the next line, you're like, what changed here? Well, the 2's gone. Oh, and that's 2 less. So they must have subtracted 2 on both sides, giving me 6x equals 24. So they use the subtractive property where you subtract a number on both sides. And then, of course, you finish it off by dividing. So we use the division property to finish solving this problem. So this is just a little way, or a little example of showing how we use the properties to justify things that we're doing. That's going to be the same idea as what we are going to be working on as we get into our first full-on proof. So right here, what we're looking at is a 2-column proof that's already been kind of filled in for us. You see, I'm building you up to where you create your own. And what we do here is we're just going to fill in the information that's missing. So it says that we have B as the midpoint of AC. Well, as you look up here at the top, that information has been given. So your justification would be that that is given. And if you notice there's another given down here, well, that's because there's more information that's given. So we'll use this information later on. But what we're trying to prove in this proof is that the segment AB is congruent to CD. When we just kind of use common sense a little bit here to think about this, if B is the midpoint of AC, that means that this segment AC is being split in half so that AB is the same as BC. And likewise, when point C is the midpoint of BD, that means that this segment and this segment will be the same. So hopefully your common sense is kind of already rolling through that if we're trying to prove that AB and CD are equal, your brain might go, well, duh, AB is the same as BC and BC is the same as CD. So that like transitive thing that we talked about before means that these two are also going to be equal, which that's exactly what we're about to show. We just have to go through line by line and prove that it's true. So what we need to do is to take this idea of B being the midpoint and how we kind of took that idea and said that AB is the same as BC, and we're just going to write that in here, that segment AB is congruent to segment BC. And we know that by the definition of a midpoint. That's what midpoints do, is it splits the line segment AC into 2 equivalent parts. So here we're starting to get that format that we're looking for, AB being congruent to CD, but we don't quite have it yet. We have AB being congruent to BC. So we need to keep going here. And the next piece we're going to use is the other given, that C is the midpoint of BD. And again, we know that because it's given to us. It's told right there. And then we use that same idea again, where if we know C is the midpoint of BD, we can say that BC is equivalent to CD. And we know that, again, by the midpoint definition. Midpoint def. So here we're ready to finish this off. We can pull these 2 pieces of information together and use that transitive property to say that if AB equals BC and BC equals CD, then we know that AB is equal to CD, or congruent to. And that's what we were trying to prove. it's good habit if you put 3 little dots in a triangle like this to show the reader that you're done with the proof. So it stands for therefore. Therefore, AB is congruent to CD, which is what we were trying to prove. It shows that you finished and you didn't just like give up halfway through the proof, right? Like this is the final line. It's what I was trying to prove. And again, I know that by the transitive property, because I use the idea that this equals that and that same thing equals something else. I could have also used substitution to say that I replaced BC with CD because I knew they were equal. So almost every time you use the transitive, you could also use substitution and vice versa. So that's the idea of a proof. If I'm being fully honest with you guys, I kind of hated geometry when I was in high school because I felt like this was just so much extra work that was just unnecessary. I'm like, I can look at it and be like, obviously. If this equals that and that equals that, then they're equal. But the whole idea here is that we're trying to formalize that. And obviously the problems are going to get harder as we go throughout the year. Common sense will always carry you through. I'm kind of tossing you some soft pitches right now, some easy problems, just to get your feet wet with this idea and get you into it. But moving forward, we're going to need this logical thinking and this formalized proof system in order to figure problems out, not just to be extra and write all of our steps out, show all your thinking kind of thing. So hang in there and just really try to understand how this system of logic works. So if you want to, you can go ahead and pause and try to go through and prove that the measure of angle 2 plus the measure of angle 1 is 90 degrees given this information. If you want to, go for it. If you aren't quite ready yet, I'm going to go ahead and take you through it. So starting out right away, we've got the angle WXY is a right angle, which is shown here in the picture. We're going to be told that angle 1 and angle 3 are congruent. So angle 3 and angle 1 are the same. So that's another piece of given information. And we're trying to prove this down here. So this is where we need to end up at. All right, so you want to start with one of your givens. I'm going to start with WXY is right angle. And I know that because it was given to me. That was the given information. Part of it, anyways. Once I have that, so one of the things you want to use to help guide you through these proofs as you're figuring them out is thinking about the structure of how you want your answer to look. So I need to say that this thing equals 90. Well, this is a good place to introduce that equals 90 because right angles equal 90 degrees. So I'm going to go ahead and take the opportunity to go WXY, or the measure of WXY, equals 90 degrees. And I know that by the definition of right angles. So there I've got part of my final proof. It equals 90, so we're a step closer. But obviously right here I have a full angle, and what I want is a sum of angles. So, I see. Maybe I want to split WXY into its two parts. See how angle 2 plus angle 3 equals WXY? So maybe I can go ahead and bring in angle addition, saying that angle WXY is equal to the sum of angle 2 plus angle 3. So again, I've brought in some of the structure that I want here in my final proof or my final conclusion. And I know that by the angle addition property. Which is something that you should have seen in your last video as well, that you have segment addition, angle addition. It's not a bad idea to make a journal or a little note catcher somewhere of all the different properties you can use so that you don't have to pull them all from your memory every time you sit down to do one of these problems. So I'm going to go ahead now and try to get this format really, really close to what I want. And I'm going to use substitution here to say that if WXY is angle 2 plus angle 3, then I'm going to put that in up here for where WXY was. So I'm going to say that the measure of angle 2 plus the measure of angle 3 equals 90. So basically I've replaced the WXY with angle 2 plus angle 3 because I know that they're equivalent. And I can do that by substitution or the transitive property, whichever one you want to use. But we're still not quite there yet. I have 2 plus 3 and I want 2 plus 1. All right, so I need to bring in this other given at this point. So the other given that I have is that angle 1 is congruent to angle 3, and that was given to me. And now I'm ready for my final conclusion. Because I know angle 1 and 3 are equal, I can replace angle 3 with angle 1, again, by substitution or the transitive property. And that should get me to my conclusion. Instead of having 2 plus 3, I'll have 2 plus 1 when I replace that 3 with the 1. So the measure of angle 2 plus the measure of angle 1 equals 90 degrees by substitution. Bang, bang, I am done. That's it right there. That is a proof. I got to the final conclusion I was trying to, and I showed every step of thinking, every step of the way. Now, again, you might have been able to look at this and deduce this really easily. You're like, well, if 2 plus 3 is 90, and I can sub out 1 or 3 with 1, then 1 plus 2 is 90, duh. That's exactly what we did here. You just had to show your thinking every step of the way, which I know is tedious, but welcome to the world of proofs, right? It's very tedious. You have to go through and show line by line so that we can confidently say what we know and don't know. Okay, here's the first one I'm going to try to cut you loose on. So you've got a given and you've got something you're trying to prove. See if you can pause the video and set up a 2-column proof, just like I did right there, to show that if we know DC is congruent with DE, and I should actually have segment bars over those. How do I figure out that BD is the same as CE? And again, maybe you can already figure this out just logically, like common sense in your head, but show the proof, show the steps of thinking that you need, and try to justify it every step of the way. Go ahead and pause the video and try that now. All right, let's look at how that went. So I started with my given that BC is equal to DE, or congruent to DE, if I wanted to be technical. And that was given to me. Now, I was kind of stuck there for a second. I was like, well, where do I go from here? I knew that I needed to introduce this segment BD, right? That's not given. Only BC is given. I need to get BD in the mix somehow. Same thing with CE. I needed to get that in there. So I thought, well, how do I get from the given BC to BD? I add on that extra bit CD. So I took BC plus CD and said that's equal. That's how you get BD, right? And you can do that by segment addition. If I take 2 segments and add them together, then you get the longer segment. And I did that again with CE. I took the given DE and added on the extra bit so that I could introduce CE into this proof, into this this problem. Then what I did is I went back and grabbed BC is equal to D, the original given, and said, okay, well, I need to get these things equal to each other somehow. So I added CD onto both sides. I took this equation right here, BC equals DE, and I added on CD to both sides. That's the same thing as what I did back here with the additive property. I took x equals 9 and added a plus 3 on both sides. Well, here I just took BC equals DE and added a line segment, the same amount onto both sides, right? CD is the same on both sides, so you're allowed to add it to both sides. And then I use substitution to say, all right, now I've got it. BC plus CD I've already defined as equal to BD. So I replaced BC plus CD with BD, and I replaced DE plus CD right here with what it's equal to, CE, because those are the segments I wanted for my final proof. So I've got it. Therefore, BD is equal to CE, and I showed every step of logic all the way through the problem. All right, let's keep going. These only get easier as you practice them. So we've got another one here. Now we're working with angles again. It tells us that DI, this segment right here, is bisecting NDH. So NDH. That means that these 2 angles right here are going to be equivalent. Angle 2 is going to equal angle 3. That information is not given, but we know that by the definition of a bisector. So go ahead and pause again and see if you can figure out how to prove that angle 1 equals angle 3, just knowing that DI bisects NDH right here. All right, so this one was a pretty short proof. However, it required a bit of clever thinking or to notice something here. So starting out right away, we were given that DI bisects NDH. So like we talked about, that means that angle 2 and angle 3 are equal, or they're congruent. I specifically use the congruency symbol because that's what it wants in the end of our proof. So I've got that pretty easily, and I know it by the bisector definition. That's what the definition of a bisector tells us, is that it splits this angle NDH into two equal parts. So angle 2 equals angle 3, or is congruent to angle 3. Now here's the twist, and almost every proof will involve some sort of twist. If you just look at those two angles right there, those two lines, I should say, angle 1 and angle 2 are vertical angles. And like we talked about back in our back in phase 1, with angles, vertical angles are always equal. So when we have angle 1 and angle 2 being vertical angles, which wasn't identified anywhere in the proof, but it is apparent here in the diagram, I can now assert that angle 2 and angle 1 also are congruent because they are vertical angles. So then I can use either the transitive property or substitution to say that if angle 3 is congruent to 2 and 2 is congruent to 1, then that means that angle 3 and angle 1 also must be congruent. And that is what we were trying to prove up here. Woo! All right, one last example. And down here, I want you to actually write out a paragraph proof. So this is, instead of using a table, you're just going to write out sentences that explain your thinking to try to prove that angle AEB is congruent to DEC. AEB, so this guy right here, AEB, is congruent to DEC, this angle over here. That those two angles are congruent is what you're trying to prove. So this one's a little lengthy. Paragraph proofs are always a little annoying because you have to write a lot. But go ahead and pause the video and see if you can write this out or figure out at least the thinking right now. Woo! All right. So looks like a lot. It kind of is, but the thinking wasn't too bad. So it's given that AEC and BED are right angles. Because they're both right angles, I know that AEC is equal to BED. I probably should have used a little more justification in there and said that that means that AEC equals 90, BED equals 90, therefore they equal each other. Since it's a paragraph proof, I kind of breezed over that and said if they're both right angles, they must be congruent. I think that logic still holds up all right. So then what I did is I took those angles and broke them down into their parts because I didn't want the whole angles. I just needed part of each, AEB and CED. So I broke AEC down into its parts, AEB and BEC, and I broke BED down into BEC and CED into its parts. Right? And in doing that, I finally introduced the angles that I eventually want to get, AEB and DEC, into this problem. Those were not originally in the problem at all. I had to create them by breaking down the larger 90-degree angles. Now I can use substitution to say that if AEC and BED were equal, then their parts are also equal. BEC and AEB are congruent or equal. So I just basically took this part right here and broke this down into its two parts, and I took BED and broke it down into its two parts and said those must also still be congruent. And then finally, I subtracted. I saw BEC was on both sides. So I used the subtraction property to subtract BEC off of both sides, leaving me AEB congruent to CED. And I guess I should be particular. It wanted it as DEC. It's the same angle, right? CED or DEC. You can reverse the order. But you always want your final bit to be exactly what it was asking you to prove. So there you have it. This is what proofs are all about, is going through and showing your logic every step of the way and trying to justify the moves that you're making along the way. So you have one quizzes to work on, but then you also, I just included a PDF because there's not really a good way to do this stuff online, right? You just have to get used to writing it out, showing your thinking every step along the way. So the answer keys provided below, just make sure that you go through and spend some time, seriously, spend some time working on this, and please ask questions. This is used in every chapter from here on out for the rest of the year. So make sure you understand how this idea of proofs works.